tutorial. For the tutorial, I think the Friday tutorial is moving to Wednesday, okay? And the Thursday moving to Tuesday 3. And the Monday is moving to Tuesday 11. So this is the replacement for tutorials, okay? And for the lab, so the lab, I think the Wednesday lab is not affected, but the Thursday lab is moving to Tuesday. Okay, so your project, if your project is due for tomorrow, then it will be due next Tuesday. Okay, either 1 to 2 or 2 to 3. Yeah, so please check the schedule before you go to tutorial or lab or lectures next week. Yeah, and the good news is the tutorials will be in 4082, so all the tutorials. The lab will be, I think your usual lab is just different time. Sorry, the same time but different day. Okay, so please check before you go to the lab or lectures or yeah. And then the second announcement is I have posted the past exam papers here, and I have provided the solution for the past exam paper, I mean the last year exam paper. Okay, so we can discuss about this like after we finish all the materials. And during the meantime, then I just opened the, the Google documents. If you have any question about exam or you have any solution, just post it here. Okay, we can share the solution. Okay, so that is about the next week tutorial and labs and review for exam and so on and so forth. And so now we go back to the lectures. So for the lectures, I think last week we started talking about multi-step methods. Okay. So we finished the Ronch-Cutter method, implicit and explicit Ronch-Cutter method. Okay. And so the difference between implicit and explicit is, for explicit you don't have to solve a nonlinear system, but for implicit method then you have to solve a nonlinear system. Okay. And now we started talking a little bit about multi-step method. And so what is a multi-step method? So the multi-step method is like, instead of using only yn to compute yn plus 1, now you have to use several, like yk for k less than or equal n. So it means that you can use yn minus 1, yn minus 2, and so on. So in this method you have to use only yn and yn minus 1, right? But in general you can go back to r step before yn plus 1. So that is called Adams-Basforth methods. And so the idea is, you write yn plus 1 as this exact integral. Okay, so this is exact integral. Because remember, yn plus 1 equal yn plus integral of y prime. Yeah, this is a fundamental theorem of calculus. And then you replace y prime by this f because it's a solution of the ODE. And then you replace or you approximate f by a Lagrange interpolation polynomials. Okay, so you approximate f by PR. PR is the interpolation polynomials that interpolate f from Tn minus 1 back to Tn minus r. Yeah, and so the Lagrange interpolation polynomials is of this form. So T minus the point the n minus I, so n minus I and I different from j, And, because the index here, n minus j, so this is n minus j, yeah? And then, so you replace f by PR. Then you have yn plus 1, it's just integral of PR, from Tn to Tn plus 1. Then you substitute the formula for PR inside, yeah? Then you have, this line, yeah? And remember, this Lagrange interpolation, you can change the variables, and you get this, yeah? So last time, I think I did some calculation to illustrate the step here. So last time, I think I did a little bit like this, yeah? So just expand this calculation a bit more. So the L star, yeah? The L star is obtained by you replace S by this transformation, yeah? So you replace, so you define S is T minus Tn over H, okay? Then L star S by this calculation, so L star, L star S here, okay? It just, because of this transformation, so T now become SH plus Tn. So you replace T by SH plus Tn, yeah, minus Tn minus I, and this is Tn minus J, Tn minus I. And then we use uniform time steps, so Tn equal NH. So you substitute in here, yeah. Then, this SH stay the same, but this NH got cancelled with this NH, yeah. So that's why you got only, so in this step, then you got only SH minus NH, right? Because, sorry, plus IH, yeah, because the plus IH, because the NH here got cancelled with minus NH here, yeah? And then divided by, so NH here got cancelled with NH here, so you got minus JH plus IH, yeah? And then you cancel H, then you got this formula, okay? So that is the formula we got up to here. So that's a product of S plus I over I minus J, okay? And then how do we move from this to this formula? Well, because now if you pull out the top part, yeah, so the top part is still I equals 0 to R, I different from J. Then we have this one, okay? And now what happened to the bottom part? What is the product of I minus J? So if we write down explicitly, okay, so if we write down explicitly, what is the product of I minus J? Yeah, I different from J, I from 0 to R, yeah? Then remember, J is between 0 and R, yeah? So in the Lagrangian formula, J is between 0 and R. So this one, when you expand it out, will be 0 minus J. Remember, J is fixed, yeah? So J is fixed. And then you have 1 minus J, and then 2 minus J, and so on. So when do you stop? Well, so remember, I different from J, yeah? So you cannot stop at J here, but should be like J minus 1, right? Because it's 0, 1, 2, then J minus 1, yeah? Then minus J, okay? And then now you start again, but you cannot take, j minus j, right? Because see it, I has different from j. So you have to start again at j plus 1, yeah, minus j. Then j plus 2 minus j. And what is the last term? So the last term will be r minus j. Okay? So agree, yeah? And now, so now, this is a product of two things. So the first one, well, maybe we just look at this one. So what is this one? So this one is like 1 times 2 times 3 times up to r minus j. Yeah? So it will be r minus j factorial. Okay? For this term, yeah? Okay? And then how about this one? So this one you will see that it will be of the form, so if you look at this one, it will be like minus 1, yeah? And then it will be minus 2, and so on, up to minus j. Yeah? So therefore, this one will become like j factorial minus 1 to the j. Okay? So that is how we get this formula. So we move from here to here. So this denominators reduced to j factorial r minus j factorials. Okay? So you can move the minus to the j to the top. I mean the sign is doesn't make any difference. But you see, this is the how we get this formula. And based on this formula, then you can compute bj. Yeah? So last time I computed, what is b0 here and what is b1 here. So we got our, suppose we use the formula, we compute. So I still have the calculation last time. So the first line, yeah. So this is corresponding to AB2. Okay, so AB2 is when R equal 1. So when R equal 1, you plug in this formula, then you have B0 and B1. Okay, so B0 can be computed by this formula. So you plug it in. So you plug it in this formula. When you plug in j equals 0. So j equals 0, then you have b0 here, minus 1 to the 0, so 0, 1 minus 0 factorials. Integral of s plus I, well, because now s plus 1 only, because, you don't have s plus 0, because 0 is j. So then it gives you 3/2, okay, and 3/2 is the coefficient here. So 3/2 here, okay. And similarly, by plugging in the formula, you got b1 is minus 1/2, so that's why you have minus 1/2 here. Okay, so those magic numbers come from these integrals. So you can do the same for r equal 2. So r equal 2, then you got AB3 methods, and r equal 3, then you get AB4 methods. Okay, so that is how we get the AB methods. So now, when r equals 0, then you just have, the Euler method. So we don't have to consider the case r equals 0 anymore. So now the claim is that local truncation errors of r plus 1 step will be OHR plus 1. So the order of conversion, depends on how many steps you look backward, So now for AB2, we can show that the order of conversion is OH squared. Yeah? So how do we prove that? So we just use the Taylor expansion, right? So this one is the Taylor expansion of y around the point T. Okay? And then, this one is the the formula come from AB2 method, yeah? So 3 half and 1 half, remember we just computed over there. Okay, you plug it in, okay? Then, because F is Y prime, yeah? Because the ODE say that Y prime is just equal F. So then, you know, you just substitute it in here. So you got, here you got Y prime at T, but here you got Y prime at T minus H, because this one F at T minus H, yeah? Then here you plug in the Taylor expansion, yeah, but this is a Taylor expansion for Y prime. Okay, so Taylor expansion around T. Okay. And then, so the local truncation errors. So remember local truncation errors, it's just, you know, this minus this. Okay? So maybe let me write down the local truncation errors. So local truncation errors is right here. So in our case, local truncation errors is so local truncation errors in AB2, yeah? So is Y T plus H minus YT over H. And remember, we have it, in our case, we have only two coefficients. We have only B0. Yeah, so we have only B0 F. And when you put in J equals 0, you just got T YT, yeah, minus B1, yeah, F T minus H Y T minus H, yeah. And remember, for AB2, yeah, because we have this coefficient, so this B0 just 3 half, so you just plug it in here. So this one becomes your 3 half, yeah. So 3 half here, yeah. So for B0. And for B1, you just have minus 1 half, so minus 1 half. So it becomes a plus here, okay? Yeah? So now I have, if I take the difference between this, you know, this equation and this equation, then I got exactly the local truncation errors, okay, on the left, okay, compare with the formula here. See, you just compare the left, yeah? And how about the right-hand side? So the left is the local truncation errors, but how about the right-hand side? For the right-hand side, the Y prime got cancelled with this Y prime, okay? Y double prime over 2H got cancelled with this one, okay? So then what you have is you just have order OH square, yeah? And that is exactly what we claim here. So it will be of order OH square. You see, so the Adam-Basford method order 2, then the order convergent OH square, yeah? By this Taylor expansion arguments. Okay, and then, so we expect that the Adam-Basford method, AB2, will give the same order conversion of Roncaster method of order 2. Okay, because Roncaster method of order 2 is still have conversion order 2. Yeah. Or you can use Horn's method. Horn's method is the order 2 method as well. So it means that you can use, you know, remember in this formula, remember this formula. So you start with y equals 0, right? So if you start with y0, then this one becomes y minus 1. So you cannot start at n equals 0 here. But you have to start at n equals 1. Yeah? So n equals 1, then this one is y0, and this one is y2. Okay? But then where does y1 come from? We cannot compute y1 by this formula. Okay? So we have to compute y1 from some other methods. Okay? And so what methods we should choose? We should choose a method that has the same order of conversion. Yeah? So for y1, you can use order 2 methods, Lagrange-Kotter method order 2, or you can use Horn's method to compute y1. And once you have y0, y1, you can compute y2 and so on. Yeah? So that is the idea. So here you can see that now suppose we try to solve this ODE by 2 methods, explicit Lagrange-Kotter method order 2 or Adams-Blatchford method order 2. Yeah? So this is the formula for explicit Lagrange-Kotter method of order 2, if you remember. Yeah? And here you can see that you don't have any problem because you don't have to solve any equation as well, because everything on the left, everything on the right is just yn. On the left is yn plus 1. Yeah? So AB2, so explicit method as well. So on the left you have yn plus 1, on the right yn. But here you have, like to look back yn and yn minus 1. Yeah? So if we run, suppose we take the y1 for AB2 method is given by the explicit Lagrange-Kotter method order 2. Then you run the 2 programs and you can see that, they give very close values to each other. Okay? Well, slightly different when time equals 1. So it gets further and further, But still, the order of conversion, for explicit Lagrange-Kotter method. But by the way, somebody asked how to reduce the order of conversion. So, are you sure that you know how to reduce the order of conversion? Somebody asked, like, how do we reduce? So suppose give you a error table like this. Can you reduce the order of conversion? Yeah? Yes? Yeah? So what happens is you just take the errors, yeah? So take the errors. So suppose I have H1 is 1/8, yeah? H2 is 1/16. Then I have error 1 is something, like 282 10 to the minus 2, right? And E2 is 7.59 10 to the minus 3, yeah? Then assume that this one is CH1 alpha. This one is CH2 alpha. Then you have H1 over H2, right? Sorry, E1 over E2. E1 over E2, yeah? We equal H1 over H2 alpha. Okay, and then you can take the logarithm. So any logarithm is okay. So any logarithm. So alpha logarithm, any base. And then from here you can deduce the order of conversion. Alpha is logarithm of E1 over E2 over logarithm of H1 over H2. So this one, it just comes from the errors table. Okay, it doesn't come from the theory. So see, from the errors table, I know those 4 values, I can deduce the order of conversion. Okay, numerically. And you can see that, numerically you see that the order of conversion is about 2, right? Because it 189, but then it close to 2, yeah, 2.01, yeah. And similarly for this method, so it close to 2, so the order of conversion numerically. So in the project, I asked you to deduce the order of conversion numerically only. I don't ask you to prove anything, okay? So don't try to prove anything in the project reports. Okay? You can prove it if you want to, but you don't have to. Okay? Yeah? So now show that the AB3 method has truncation errors of order OS3. So let's see whether I can do it. So we have time or not. So how do we show this? So remember local truncation errors. So go back to the general formula of local truncation errors. Yeah. So now we have T will be y t plus h minus yt over h minus, and now AB3. So you should have three terms. Yeah. So B0, B1, and B2. And where do we get it? So from this one. Okay, from this AB3 method. So it will be minus h over well, we divided by h already, so it will be 23 over 12 f at the yt, yeah, and then plus 16 over 12 f t minus h yt minus h, yeah, and then minus 5 over 12 f of t minus 2h yt minus 2h. Yeah, so we just use exactly this formula. Okay, but with respect to r equal 3, so you have to replace this one by b0, b1, b2. Yeah. Sorry, respect to r equal 2. Yeah. And so now, so we try to apply the same ideas here. Okay, so you have yt plus h minus yt over h. So this one will be exactly the same here. So we just have y prime. So this one is just the expansion plus y double prime over 2h y triple prime over 6 h squared, right? And some OS3. Okay? Well, actually, maybe we should do one more, yeah? So it would be maybe y fourth derivative over 24 h cubed plus OH4. Yeah, so 24, just 4 factorials, yeah? And now, what is the other terms? So you have, so 23 over 12 f at t yt, yeah, minus 16 over 12 f t minus h yt minus h. Okay, and then minus become plus 5 over 12 f t minus 2h yt minus 2h. So now you see Taylor expansion, right? So now you have, so this one will be, so this one is the right hand side, yeah? So what was the other term, yeah? So this one will be 23 over 12. Then you have y prime, okay? Y prime because f equal y prime, yeah? And here, now you have 16 over 12. Okay, and now you have, similarly here, just the coefficient different, but now you have y prime t, yeah? Because this one is just y prime at t minus h, yeah? So y prime at t minus h. Okay, and then this one is just 5 over 12 y prime at t minus 2h. Okay, and now you use Taylor theorem again. So you use Taylor expansion again. So this one is y prime at t. This one is 16 over 12. And remember, this is the Taylor expansion. You have y prime t minus h. So y double prime th plus y triple prime th square, and where we go to h3, yeah, so we have to make one more term, so minus 1 over 6 y to the fourth derivative h cubed, okay, and plus some higher order term. Yeah? And now we have to do the same for the last term, so 5 over 12. And this one is y prime at t, okay, minus y double prime 2h, yeah? So because we have 2h here, yeah? And then plus 1/2 y triple prime 2h square, yeah? And minus 1 over 6 y to the fourth derivative 2h cubed, and plus some higher order. Okay, so now we just see whether we can have some cancellation. So now for y prime, so look at for y prime. So you have 23 over 12 minus 16 over 12 plus 5 over 12 for y prime. So does it cancel y prime or not? So it doesn't cancel. Something. So 28. Which one? Yeah, we have to subtract from here, right? Which one? So if we subtract this one, yeah? So this one, okay, so this one will be 28, yeah? 28 minus 16 over 12. So it will be 12, right? Okay, so it's cancelled, yeah, so it does, yeah? So this one will cancel with this one. Because you have to subtract. You have to subtract with this one, yeah? So this one does cancel, yeah? For y prime. Okay? And then how about y double prime? So for y double prime, then you have so for y double prime, so we just look for this one, yeah? So y double prime h, actually y double prime h, yeah? So it will be plus 16 over 12, yeah? 16 over 12, and then, so this one is minus 10 over 12, yeah? Okay? So then this one will be 6 over 12, so 1/2, yeah? So it does cancel. So it does cancel with this term. Okay. And similarly, I think you can compute for y triple prime h square. So for y triple prime h square, okay, you can have so y triple prime h square you have, so this one, yeah, multiply this one, so it will be minus 16 over 24 and plus how many? So plus, so this one is 4 over 2, so give you 2, yeah? So 2 times 5 is 10, yeah? So 10 over 12. So it will be minus 16 over 24 plus 20 over 24, yeah? So it gives you 4 over 24. So what is 1 over 6? So it does, yeah? So it does cancel with this one. See? So you got the constant cancel, h square cancel. So you have to have h squared, right? So we just forget about the explicit constant for h squared, but it will be order h squared. So you get the idea, right? Yeah? So then we just prove that the truncation errors for AB3 is order h squared, right? Because the constant cancel, the h cancel, h square cancel. So the remaining is just OH squared. Yeah? So you get the idea, right? So I mean, this one is just the explicit calculation, but that is what is happening, yeah? And you can do the same for AB4. It's just tedious calculation, but it could be done, yeah, the same way, yeah? And so now, so how about another method? It's called Adams-Moulton method. So Adams-Moulton's method is similar to Adam-Basford in the sense that it's a multi-step method. However, the difference is you start at Tn plus 1. So remember in AB method, you start at Tn and you go back, but here you start at Tn plus 1 and you go back, and see when you go back R step, then you step at, you start the starting point is Tn minus R plus 1. Okay? And so the formula for the polynomial is slightly different. So now J doesn't run from 0 to R like before, but it runs from minus 1 to R minus 1. Okay? And you plug it in again. Okay? And then, you know, we can use the same tricks to get out the formula for Bj. You know, remember just the integral of the Lagrangian. We just skip a lot of steps here. But now, what is the key difference? So now if you look at the key difference. So what is the key difference here? So is it an explicit method or implicit method? Implicit, yeah? Why is that?
Because the j is minus 1.
Yeah, because when j equals minus 1, then you have yn plus 1. You have yn plus 1 on the left and on the right. Implicit method. Make your life, you know, difficult because now you have to solve a, you know, nonlinear system. Or use fsolve, okay? Fixed point iteration, whatever. But you see, the difference is now it's become an implicit method. Okay? So idea is the same, but now when you make slightly modification, you have an implicit method. And so for R equal 1, you have this formula. So we just skip the how to compute those coefficients. Now it's become a magic numbers, yeah? So you got the left and the right, yn plus 1. The left and the right, you have yn plus 1. So this one is order 2 AM methods, order 3 AM methods, order 4 AM methods. Yeah? Okay, so like before, you can consider the local truncation errors, and you can show that, you know, the local truncation errors for AM2 will be order OH square. So I just skip the proof, but you know, I mean, the idea will be the same. You just use the Taylor expansion, okay, again and again, and plug in some formulas and calculation, and then you get out the local truncation errors of AM2 will be order OH square. Okay, so now, so the last topic will be maybe let me explain this a bit more. Yeah. So now, so what does it mean here? Suppose the function f is of the form linear like this. So ay plus b and a and b could be depends on time. Okay. Then actually, for I think this one should be AM2. Yeah, should be AM2. So let me go back to AM2 method. So suppose you have AM2. Yeah. So let me explain this a bit more. Look a bit unclear, but so suppose you have AM2 method. Yeah. So the formula is yn plus 1 is yn plus h over 2 f tn plus 1 yn plus 1 plus f tn yn. Yeah. And now, what happens if f takes the special form? So f takes the special form ay plus b. Yeah. So a and b can depend on time. So capital A, capital B can be a function of time. Okay. Then when you plug it in AM2, okay, then you have yn plus 1 will equal yn plus h over 2, and now, you know, it's become a tn plus 1 yn plus 1, yeah, plus b, because I replace f by this. Okay, so this become this. Okay, and then this one, so b will be at tn plus 1, yeah, and then this term will become a tn yn plus b at tn. Okay, and now you can rearrange it so that you move everything with respect to tn plus 1 to the left. So you got yn plus 1, move the atn, so a h over 2, well, this one should be h over 2 a tn plus 1 yn plus 1. Yeah, I just move this guy to the left. Yeah, and then h over 2 b tn plus 1 to the left as well. And then on the right, what you have left is just yn plus h over 2 a tn yn plus b at the end. Yeah. And now, so this one you can take yn plus 1 to be the common terms. Yeah. So you got 1 minus h over 2 a tn plus 1 minus h over 2 b tn plus 1 equal yn plus h over 2 a tn yn plus b tn. Yeah. So what does it mean here? So this means that you can solve for yn plus 1 explicitly. So I move this to the so if I move this one to the left again, yeah. So because this term doesn't depend on ytn, so I move it to the left again. So move this one to the right again, yeah. So still 1 minus h over 2 atn plus 1 equal yn and plus h over 2 and atn yn, and this one is btn plus tn plus 1. Okay, and then now you divide it, and then you got yn plus 1 is the whole thing here, 1 minus h over 2 atn minus 1 plus 1 minus 1, and then yn plus so essentially I will get this one. Okay, I will get this one because I combine this term and this term. So I got yn h over 2 atn yn and plus h over 2 btn plus 1. So what does this slide say? So this slide says that when f has a special form like this, then actually you can rewrite the implicit method as an explicit method. Right? So this one is a typo. So this one should be AM2, not AB2, yeah? You see, according to the calculation here, you eventually see that yn plus 1 can be defined explicitly based on yn. Yeah? So that is exactly this one. So what it means by you can solve yn plus 1 directly. So when f has a special form like this, f is ay plus b. Yeah? Then you can solve for y plus 1 explicitly. Okay, so I just expand the calculation, to explain why I get this formula. Maybe I should plug it in the lecture notes rather than just give you the final answer like this. But it's come from this, yeah. But in general, I mean, when f has a general nonlinear form, then you cannot solve it explicitly. And you have to solve a nonlinear system. But when you try to solve a nonlinear system, like you saw in the project, then it takes a long time, right? So you put in fsolve every step, and if you increase the number of iterations inside fsolve, you decrease the error tolerance, and it might take forever. So then people came up with the predictor-corrector methods, which is the combination of the two explicit-implicit methods. So predictor-corrector method is something like this. So you use, you use an explicit method to make a prediction for yn plus 1. Okay? And then you use the implicit method to compute yn plus 1 explicitly. Exactly. So in this sense, then you don't have to solve a nonlinear system at every step. Okay? Because if you look at this formula, so Pn plus 1 can be defined based on the yn and yn minus 1. Yeah? And then after you got Pn plus 1, you plug it in here. Yeah? Then everything is explicitly defined, so you don't have to solve any nonlinear system. Okay? And you still have a high order conversion. So that is the idea of predictors corrector method. So maybe we can talk about this one a bit more next week, yeah, for the last two lectures. So finish it off and then review for the exam.